Hello students, in this video we'll prove the strong law of large numbers under the assumption that the random variables have finite fourth moment. Let's be given random variables IID, that are IID, with finite fourth moment. What that means the expected value of x1, since this in distribution to the power 4, is less than infinity. Okay. Then the strong law of large numbers asserts that the probability that the limit as n goes to infinity of x1 plus all the way down to xn over n, that's the sample mean, right, converges to mu. This happens with probability 1. Okay, that's what the strong law of large numbers says. The weak law of large numbers has the limit on the outside over here. So what we have over, it says that it converges in probability, but we have a stronger condition over here. It says the limit exists. This limit will exist in equal mu with probability 1. So this random variable is going to converge. This is a random variable over here. It will converge to a constant with probability 1. That constant is just the common mean of the random variables. Okay, so of course the standard trick what we're going to do is I'm going to assume without loss of generality that mu is equal to 0 because I can subtract off n copies of mu over here. By subtracting off a mu over here, a mu over here, and a mu over here, I can put a 0 over there. So I can center the random variables. We can assume without loss of generality, assume the expected value of xi is equal to 0. Okay, so we're going to assume that. All right, so now what I'm going to do is I'm going to consider these sets, consider the set, let's let epsilon be greater than 0, and consider the set of all points omega, such that what? Such that Sn is just the partial sums. Okay, so we're going to do so Sn in absolute value. Sn is bigger than or equal to epsilon times n. Okay. Sn of omega. Where of course, what's Sn? Sn is just the sum of the xi, right? So here Sn is our notation. So Sn is x1 plus xn, the random walk. Okay. Now, what can I say? So I'd like to estimate the fourth power of Sn. So what is the fourth power of Sn? So if we look at Sn to the power 4, that's what? That's the sum. J goes from 1 to n of xj to the fourth power. And of course, what will that be? That's going to be the sum, 1 less than or equal to I, j, k, and l, less than or equal to n. So I have 4 indices of xi, xj, xk, and xl. Okay? I'd like to estimate the expected value of this thing. And so when I estimate the expected value of these things, what are the terms that can arise in this sum? So let's classify the terms when I do this thing. So when computing the expected value of Sn to the fourth power, what terms will arise? We have terms that look like this. We have n terms that look like the expected value where all the indices are the same, where I, j, k, and l are all equal to each other. That can occur n times. Expected value of x1 to the fourth. We have n of these terms over here where all the indices are the same and the common index could just be 1. So I'd have x1 to the fourth, x2 to the fourth, x3 to the fourth, xn to the fourth. So there's exactly n of those terms. We'll have terms of this form, terms, and we'll have how many terms? I'm going to have n choose 2, and then 4 choose 2 terms of the form expected value of xi squared, quantity squared. That will occur from what? That will occur from terms in the product that look like xi squared, xj squared. Then using the independence of these things, the expected value of these terms over here, when you have two of the indices being the same, so from n of the slots 1 through n, choose two of them, I and j, and then from the 4 of I, j, k, and l, choose two of them. That gives me that many terms, and those terms will since you have a finite fourth moment, you also have a finite second moment, so these terms are bounded as well. Okay, so I have terms of those form. Then every other term is going to have at least one factor of x, a single factor of xi. So they could all be, let's do the example, they're all distinct. If I, j, k, and l are all distinct, then the expected value of that thing will be, by the independence, the expected value of xi, the expected value of xj, expected value of xk, expected value of xl, which is 0. So the terms when there's exactly one sort of isolated, if I have three of the same, if I have an xi, 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 and an xj, the expected value of that is going to give me 1 in the expected values of xl. So the other terms are 0, as they have at least one expected value of xi, which is 0 by assumption. Okay. So in other words, let's count how many terms we have. This is, of course, these things are bounded over here. These things are bounded over here. So let's count in terms of n how many things these are. So these things, this behaves like n squared. So that's of order n squared. And so what we've just shown over here is that the expected value, so from this estimate, we can conclude that the expected value of Sn to the fourth is less than or equal to a constant times n squared. Okay, so that's the estimate we've achieved. And so now what can I conclude about this set over here? This set, I'll call that set an epsilon. Well, the probability of an epsilon is going to be, by Chebyshev, is going to be less than or equal to the fourth moment of this thing over here. So it's going to be Cn squared over this quantity over here to the fourth power, right? So that's the Chebyshev estimate. So this is going to be epsilon to the fourth, n to the fourth. And this thing is of order what? This is less than or equal to some new constant c tilde, which depends on epsilon, n to the negative 2. So in other words, the sum of these probabilities is finite. The sum, n goes from 1 to infinity, of the probability of the an, epsilon, is less than infinity. And so by Borel-Cantelli, we have that the lim sup, the probability of the lim sup, as n goes to infinity, of an epsilon is equal to 0. So in other words, this estimate, the set where Sn is bigger than or equal to n epsilon, can only happen finitely many times. That's great news for us, because now what can we do? We can define these, I'm going to call these sets these lim sups. These lim sups over here, I'm going to call these sets B and B. I'm going to call those B epsilon for the lim sups. So here B epsilon is the lim sup as n goes to infinity of an of epsilon, okay? And so the probabilities of B epsilon, the probability of B epsilon is equal to 0 for every epsilon. Probability of B epsilon is 0 for all epsilon greater than 0. Beautiful, okay? And so what's happening? So B epsilon, as epsilon tends to 0, B epsilon, the sets B epsilon, get bigger and bigger and bigger and bigger and bigger because of this, the set where the lim sup is Sn is bigger than smaller and smaller and smaller and smaller numbers. B epsilon increase to the set where Sn over n does not converge to 0, okay? So now we're done, because what I can do now is I can say the probability that Sn over n does not converge to 0, okay? That's what we like to show. We'd like to show that this goes to 0, right? That's our objective. Sn over n does not go to 0, is contained in the union of all these, a collection of these Bn, right? So this is less than or equal to the sum, k goes from 1 to infinity, for example, of the probability of B 1 over k, for example, right? Because the B 1 over k, The union of those b1 over k's as k goes from 1 to infinity will give me this set where it does not converge to 0. And for each k, these are equal to 0. So the sum is equal to 0. So the probability that Sn over n does not converge to 0 is less than or equal to 0. Therefore, the probability that Sn over n does not converge to 0 is 0 itself. Therefore, the probability that Sn over n converges to 0 is equal to 1. And that is the strong law of large numbers. Now, notice over here I've assumed finite fourth moment. And of course, the question becomes is, can I loosen this restriction a little bit? So in other words, where did I put that condition over here? Can I loosen this restriction? The answer is yes. What we need to do is we can actually loosen this restriction all the way to saying it has a finite first moment, but we need the Kolmogorov maximal estimate to do that. And we'll see that in further videos. Thank you very much.